We're going to take this screencast to look at how a few different functional groups present in mass spectrometry, and we are also going to talk about a coupled technique at the very end of this screencast. So most elements have one major isotope, but chlorine has two really common isotopes, chlorine 35 and chlorine 37, which occur naturally in a 3-to-1 ratio. So what you're going to see in the mass spectrometer then is you are going to see, instead of a M+1 peak, and it's still there, it's just really small, you are going to see a big M+2 peak. And the height ratio is what tells us this is chlorine, because this chlorine here, this peak due to chlorine here, is 3 times as big as that peak. And so what we know is the larger peak, right, is going to correspond to the compound containing chlorine 35. So that's going to be our M peak. And then the compound containing chlorine 37 is going to be our M+2 peak. Okay. So whenever you have a molecular ion that has two peaks, an M and an M+2 peak in a 3-to-1 ratio, a chlorine atom is present. Now, I also want us to look at bromine. Bromine has two common isotopes as well, bromine 79 and bromine 81. But the difference is these occur in a ratio of 1-to-1. So bromine is also going to have an M and an M+1 or M+2 peak, but it occurs in a ratio of 1-to-1. So these peak heights are about the same. And so what we see here is that bromine 79 is going to be your M peak, and then bromine 81 is going to be your M+2 peak. Now, we've already talked about this in a previous screencast, but I want to review it just a little bit. A lot of chemists use mass spectra to determine only a compound's molecular weight and molecular formula, but we can get a lot of useful structural information from these fragmentation patterns. And in functional groups, some functional groups exhibit really common fragmentation patterns that make it easy to identify if that functional group is present in the molecule using a mass spectrum. So one of the things to be aware of, a really common fragmentation that we see, is a loss of a CH3 group here, and that's always going to be 15 units less than the molecular ion. So if you lose 15, that's a really good indication that you've lost that CH3 group. And we can see it as we go through here that these all differ by 15. So they sequentially lose a CH3, or they differ by 14 and they lose a CH2 group. And so we see that as we go through. Now, this is hexane, and I walked through this in the previous screencast of this cleavage pattern where we see how it cleaves here. And so that's a really common cleavage of hydrocarbons. I want us to look at some other fragmentation patterns of other functional groups. So let's look at carbonyls for just a second. If you have aldehydes or ketones, and I want you to remember that ketones will have two R groups, and an aldehyde will have an H here. And so this R prime is it can be, right, it's what it's saying is, look, it's different than this R, or it can be the same. And this R is going to be a hydrogen or an alkyl group, which is just those carbons and hydrogens. Now, this can undergo an alpha cleavage between the carbonyl carbon and an adjacent carbon. And that's going to yield a neutral radical over here and a resonance stable acylium ion here that gives a really specific pattern in the mass spectra. So let's talk about how this can be used. Let's say you have benzophenone here, right? And you bombard it with electrons and all of a sudden you have this mass peak at 105. That's going to be from this bond breaking and there now being a C double bond O group. So that fragmentation pattern with this molecule would tell you, hey, look, we started out with an aldehyde or ketone. Now, alcohols also have a specific cleavage where, again, it's going to break between the alkyl group, which is shown with an R here, and the carbon bearing the oxygen group, and it gives a resonance stabilized carbocation. And so this is an example of that. And so if you saw a peak in your mass spectra that looked like this, that would indicate, hey, look, we probably have an alcohol group. Alcohol can also undergo dehydration to form water in a radical cation. So a lot of times you see with alcohols, you'll see the loss of 18 because it's an oxygen and 2 hydrogen atoms that have been lost. So this would, for example, be the loss of 18, and that helps you identify, hey, look, this is probably an alcohol functional group. Amines give a really interesting functional group, kind of cleavage here. They break the bond between the amine here and this R group, and they form an alkyl radical, which is uncharged, and then a resonance stabilized carbocation here. So, for example, if we had trimethylamine where we're going to break this bond, it would be the loss of a CH3, and we would see this resonance stabilized cation, and so you would see a loss of 15 here. So 101 minus 86 is that loss of 15 to see that CH3 group there. It's not always a CH3 group. It just sort of depends on what is on the carbon next to that nitrogen. Now, we can have a lot of what we deal with are low resolution mass spectrometers that report the mass to charge values to the nearest whole number, but you can also have high resolution mass spectrometers that measure the mass to charge ratio to 4 or more decimal places. And so you can see the different isotopes and their masses to 4 or more decimal places. What this helps us do, for example, is if we have 3 molecules here that all have, when we look at the whole number, a mass to charge equal to 60, if we use a high resolution mass spectrometer, we can narrow down whether it's going to be C3H8O or C2H4O2 or C2H8N2, right? By looking at those more specific decimal places of the isotope. So that gives us it's a really helpful tool. It gives us a lot of differentiation. The other thing that makes mass spectrometry really interesting is it can be combined with gas chromatography into a single instrument. So what do we mean by this? So if we look here, this is a schematic of something called a GCMS or GC mass spec, but it's a gas chromatograph coupled with a mass spectrometer, right? And so when we talk about a gas chromatograph, it's going to be a thin capillary column. So we have a thin capillary column here, and it contains a viscous high boiling liquid, and it's all kind of housed in an oven. So it looks like a big white box. And when you inject a sample into the GC, it's vaporized and it's swept by inert gas through the column. And those components are going to travel through the column at different rates. And they're often separated by boiling point, with your lower boiling point compounds exiting the column before the higher boiling point ones. So what this does is it separates your mixture so you can analyze it individually and gives a really beautiful mass spec. So each component, as it comes off the column, enters the mass spectrometer where it's ionized and it forms that molecular ion and then the lower molecular weight fragments. And so that records, right, a GC, which looks like this. So this would be your mixture and these would be your peaks. And then, right, where we have the retention time here and the peak intensity, and then you can look at each individual peak and identify the substance. So for example, if this was a mixture, you could say, okay, well, this is, hexane, and this is octane, and so on and so forth. And so it's a really versatile method to use. So that's kind of interesting. If we look at an example of this, if you were to analyze a urine sample for THC, which is the active component in marijuana, the organic compounds are extracted from urine, then purified and concentrated, and then injected into the GC mass spec. And so then your THC appears as a GC peak, and the mass spectrum is here at 314, which is its molecular weight. So I've had former students who've gone and worked in TBI labs, and they've used GC mass spec for kind of this method. And then I've also had students who have gone and worked for the state and analyzed blood samples using this method as well. So super versatile, and it's used in industry quite a bit. If you have any questions, please feel free to stop by my office. And again, we'll be working some of these problems in class.